this next section, we're going to look at area between curves. Basically, to find the area between two curves, f and g, over an interval from a to b, where f is greater than g. So we're looking at a picture that looks something like this. My f is always bigger than my g over the interval. Then we can say that the area is going to be the integral from a to b of f of x minus g of x dx. Another way to think of that is I'm going to evaluate the integral of the upper curve, so finding the area below the f curve, which would be everything above the x-axis between a and b, and then I'm going to subtract off the area below g. And what will be left over is this shaded region, f minus g over the interval. Okay? And so we're going to look at a few examples where we are finding areas of curves like this. And then we're going to look at the cases where f is not necessarily less than g. So maybe it changes places with the other function over the interval. Okay? Or maybe it's below the x-axis. So we'll look at both those cases. Okay, so this first example, we are given a region. It's bounded by the curve y equals x plus 6 and y equals x squared. And we want to find the area of the shaded region. Okay, so again, the first thing I'm going to have to do for this type of problem is figure out my a and b. Okay, so I need to know what these bounds are on my curve. Okay? And as we can see, this is going to happen where the two curves intersect each other. So to find a and b, I'm going to set the curves f and g equal to each other. And solve for x. Okay? So in this case, x plus 6 will have to equal x squared. Well, this is basically a quadratic, so I can move everything to one side. And we can see that this will factor. So x will equal 3, or x will equal negative 2. Okay? So there's my lower bound, my a, and my upper bound, b. Now that I have my limits, I want to set up my integral. So that's step 1. Step 2 is to set up my integral. Okay. So in this case, again, I want my upper curve minus my lower curve over the integral. So integral from a, which in this case is negative 2, up to 3. My upper curve stays the same for the entire region. So my upper curve is the x plus 6 minus my lower curve, which in this case will be the x squared. I'm going to integrate that with respect to x. Now this one is nice enough I can just drop the parentheses and use my basic properties. So my antiderivative is 1/2 x squared, excuse me, plus 6x minus 1/3 x cubed. We want to evaluate that whole thing from negative 2 to 3. Okay. And now remembering our fundamental theorem, says that we're going to evaluate at the upper minus the lower. So we'll take 1/2 of negative 2 squared plus 6 times the negative 2 minus 1/3 of the negative 2 cubed. That's at my So plugging in my upper limit, we'll get 1/2 of 3 squared plus 6 times 3 minus 1/3 of 3 cubed. At our lower limit, Plugging in the -2, we'll get 1/2 of 4 plus 6 times the -2 minus 1/3 of the -2 cubed. Okay. Now it's just a matter of evaluating. So we'll get a 9/2 plus 18 minus, looks like 27/3, which is 9. Minus at the lower limit, again, be careful here, make sure you distribute through. So we'll get a -2, there's a -12, so that'll be plus 12, and then a positive 8/3 being subtracted. So combining terms, looks like 30 minus 9 is 21, minus 2 looks like 19, plus 9/2 minus 8/3. And get a common denominator. Of 6. And simplifying, see that there would be our area of our shaded region. In this next example, let's find the area of the shaded region. And in this case, we're going to look at two curves where one is not always greater than the other. Okay. So in our graph, in our picture here, we have y equals 2x, which is just the straight line. And then we've got a cubic equation, y equals x times x minus 3 squared. And we want to find the shaded region. And so notice in this case, because the upper and the lower curves change over the interval, I actually am looking at kind of two separate regions. Okay, so again, the first thing I want to do is I want to find kind of those intersection points. Okay, and again, to do that, I'm going to start by setting the two equations equal to each other and solving for the intersection points. So here we're going to let 2x equal x times x minus 3 squared. Okay. And so to solve, again I want to move everything to one side since I have x's on both sides. So, and I'm going to go ahead and FOIL this out because we're going to probably need that to be FOILed. So here if I FOIL that out, I'm going to get an x cubed minus a 6x squared plus a 9x, and then I'm going to subtract off the extra 2x. And so here, combining like terms, we can see this is x cubed minus 6x squared plus 7x. Again, to solve for x, I'm going to go ahead and just factor. So I'll pull out an x, and we'll get an x squared minus 6x plus 7. And we can see here that this quadratic is not going to factor nicely, so we're going to need to use our quadratic formula, and we can see that our solutions will be x equals 0 from there, and x will equal 6 plus or minus root 6 all over 2. Okay. So there's our three intersection points. Okay, and again, on here we can kind of see there's our x equals 0. This one here will be the 6 minus root 6 over 2. And this one will be the 6 plus root 6 over 2. Okay, so there's our three intersections. So to set up our area formula, we're going to do these in two separate pieces. So for the first one, we can see that the integral is going to go from 0 up to the 6 minus root 6 over 2. And again, it's our upper curve minus our lower curve. Our upper curve in this case is the x minus 3 squared, minus the lower curve, which is the 2x. And then for the other piece of the shaded region, we're just going to add that on. So it's going to be plus the integral from the lower bound to the upper bound. So 6 minus root 6 over 2 to the 6 plus root 6 over 2. Again, upper curve minus lower curve. So 2x minus the x times x minus 3 squared. Okay. So there's our setup. And just like before, now it's just a matter of evaluating the integrals to get our area. So here again, nicely, if I look at that, it doesn't look like it's going to find the antiderivative using our basic properties. But we can come back over here and we know that when we subtract the 2x, there's the polynomial that we're looking at. So I'm just going to rewrite this. So this is going to be the integral from 0 to 6 minus root 6 over 2 of x cubed minus 6x squared plus 7x. Likewise over here, notice again the only difference here is a sign change. So if I want to do the same thing and write it in a polynomial form, the only thing that's going to change is the signs on the terms. So I'm going to get a negative x cubed plus 6x squared minus 7x dx. Now I can go ahead and use my basic properties to evaluate the integral. So I'm going to get a 1/4 x to the 4th minus a 2x cubed plus 7/2 x squared. That piece is going to be evaluated from 0 to 6 minus root 6 over 2. Plus, on the other side, again, the antiderivative is very similar with the difference of a minus sign. So it's going to be a negative 1/4 x to the 4th plus a 2x cubed minus 7/2 x squared. That one's going to be evaluated from 6 minus root 6 over 2 to 6 plus root 6 over 2. Okay. From there, it's just a matter of evaluating at this point. Okay. So here we can see when I evaluate, I'm going to get 1/4 at my upper limit. 6 minus root 6 over 2 quantity squared, to the 4th, minus 2 times that quantity cubed, plus 7/2 of that quantity squared. So there's my upper limit. Notice at my lower limit, if I plug in 0, everything is going to go to 0. For that second integral, when I go to evaluate, same thing, it's going to be an upper minus a lower. So at my upper, we'll have a negative 1/4, 6 plus root 6 over 2, quantity to the 4th, plus 2 times that quantity to the 3rd, minus 7/2 of that quantity squared. And this is going to be minus at the lower limit. When I plug in, basically the same thing, the only difference is that sign change on my terms. Okay, so now it's just a matter of evaluating. This is going to take a little bit of work, but if we go ahead and evaluate this first integral, so again, the brackets minus 0, we see that we're going to get 9/4 square root of 6 minus a 51 over 16. And if we evaluate the other two, some nice things will happen. Some of the terms will combine, and some of the pieces will cancel out, and we'll end up with just 9 square roots of 3/2. And we can simplify that. We don't like the roots in the bottom, so we'll go ahead and rewrite that. So this looks like a 9/2 square root of 6, which we can get a common denominator there. I'm just going to bring it right over here. So getting a common denominator, we'll have an 18 plus the 9, so it looks like 27 square roots of 6 over 4 minus our 51 over 16. Okay, so there's our exact area. Again, for things like WebAssign, you can plug this into a calculator and get the decimal. Okay, problems like this, excuse me, problems like this you will see in WebAssign. Ones with not so nice boundary points like we've seen here, you're probably not going to see on an exam. Those will usually have nice intersection points, because you should be able to do something like this with just factoring and then using the integrals or the values to set up the integrals and then find the answer by hand. So you're not going to see something with 4th powers of these lovely roots on an exam, but you should expect them on some of the homework and the WebAssign. So here we're going to look at one last example, and in this case, this is unlike the first two examples where you were given the picture and you just had to come up with the boundary points for your integrals. In this case, we are actually given the equations and we need to set everything up from them. Okay? So in this case, we want to find the area of the region bounded by the curves y squared equals 4x and y equals 2x minus 4. Now again, the difference is I don't know what the picture looks like. So just looking at the equations, I don't know that my upper curve is the same over the entire interval, or whether there's going to be a change. Okay? And so here, this is one where you're definitely going to want to start by graphing. Okay? So if I look at my region, let's start with the linear equation, because that one's usually the nicer of the two to graph. So y equals 2x minus 4. We know that's got a y-intercept at negative 4, and the slope for that is going to be up 2 and over 1, or it has an x-intercept at 2. Again, you can see that. So for this first curve, I'm looking at the straight line that goes through those points there. Clean that up a little bit. There we go. Okay, so there's my y equals 2x minus 4. Okay, for the other curve, I'm looking at y squared equaling 4x. Now the first thing you should notice here is this is not a function of x. This is a function of y. So another way to think of this is x equaling 1/4 y squared. Okay, well, y squared is a parabola that sits on its side. So here, notice the point 0, 0 still satisfies that. But if I put in, say, x equals 1, notice I'm going to get two different y values. I'm going to get positive 2 and negative 2. And so here, I'm actually looking at a parabola that does something like that. Okay? And so I can see on the picture that the region I'm looking for is the one in between these two pieces here. Okay? Alright, so to set up my integral, again, the first thing I notice is if I try to do an upper curve minus a lower curve, Well, that's kind of problematic for part of the interval, because from here over, the upper and the lower curve are the same curve. Okay? So in this case, instead of looking at an upper minus a lower, again, part of the interval has top and bottom curves the same. Okay, so what that means is when I go to set up my area, I want my area, I'm going to call it C to D because now I'm looking in terms of y values, and I'm going to have this be some function of y minus some other function of y with respect to y. And the way I'm going to choose these functions is I want f to be the rightmost curve and g to be my leftmost curve. So I'm going to take the right minus the left, and I'm going to look at the limits in terms of y. Okay. So in this picture, again, I need to start by figuring out where my intersection points are. So again, I'm going to set my equations kind of equal to each other. Now here I've got to be a little careful because one of them is a y squared and the other is a y. But notice, if y squared equals 4x, like we said, x is 1/4 y squared. So I can plug that in to my other equation, and solve for y. Okay, so here we'll get a y equaling a 1/2 y squared minus 4. Moving everything to one side, 1/2 y squared minus y minus 4. You can go ahead and multiply through by 2 just so we can get rid of that fraction. And we can see this will factor nicely to y minus 4, y plus 2. Okay, so y will equal 4 or y will equal -2. And that makes sense. If I look down here on my graph, that's about at y equal -2, and up here this intersection point is about at y equals 4. Okay. So there's my limits for my integral. Those are going to be my c and d. And again, if I look, my rightmost curve turns out to be my y equals 2x minus 4. And my leftmost curve turns out to be my y squared equaling 4x. Okay. Now the other thing to keep in mind here is in my formula for these, I want my functions to be in terms of y, which means I'm going to have to rewrite these so that they are in terms of y. Okay? This one's not too hard to rewrite. Here we have already seen we can rewrite this as 1/4 y squared equaling x. This one, it's a linear equation, so again it shouldn't be too hard to rewrite. We can see that this one will become x equals y plus 4 over 2. Or 1/2 y plus 2. Okay, so we're going to use those as our f and our g, and now we can set up our integral. So our area is going to look like the integral from -2 to 4, so our limits in terms of y. Our rightmost curve, which is going to be 1/2 y plus 2, minus our leftmost curve, which is the 1/4 y squared. Here again, we're integrating with respect to y. Okay. So, taking our antiderivative, again, x's and y's, just different variable. I'm going to take the antiderivatives the same way. So, antiderivative here is going to be a 1/4 y squared plus 2y minus 1/12 y cubed. And we're going to evaluate that from -2 to 4. Okay. So plugging in at our upper limit, So plug me in for 4, we'll get a 1/4, excuse me, of 16, plus a 2 times 4, minus 1/12 of 64. At our lower limit, plug me in the -2, we'll get a 1/4 of 4, plus 2 times -2, minus 1/12 of -8. Okay. Simplifying, looks like 4 plus 8. We'll pull out 4s there, so we'll get a 16/3. Minus at the lower limit, again, don't forget to distribute. So we'll get a -1 plus 4 minus 8/12, which we can reduce to 2/3. Okay. And now simplifying, looks like 15 minus 18/3. 18/3 is just 6, so our area is going to look like 9. Okay. So for these area problems, it doesn't matter whether my function is in terms of x or my function is in terms of y. If it's in terms of y, you just have to adjust it a little bit. So you'll have to solve for your limits in terms of y, but you also have to solve for your functions in terms of y, and then set up your integral accordingly. One thing to keep in mind for all of these area problems, your notation is very important. One homework, one exams. If you leave off the integration variable, meaning dy or dx, or you leave off your limits, you will be marked off. Those things are very important in setting up your integral, because once I change the limits or I change the integration variable, it changes my problem. Okay, so make sure you have your correct notation on these when you go to work out your area formulas.